In this video, we'll cover generalizing from samples to populations. Specifically, we'll go over confidence intervals using the t-distribution and confidence intervals for proportions. We'll start with confidence intervals using the t-distribution. And as an example, I'll use question number 22 from chapter 6 of your textbook. This question states, a local police department attempted to estimate the average rate of speed of vehicles along a strip of Main Street. You'll notice that they use the Greek character mu. The reason they use the Greek character is because the researchers are interested in the population mean. That is, the mean speed of all vehicles traveling along Main Street. However, they are not going to measure every vehicle. Instead, they'll select a sample. Specifically, with hidden radar, the speed of a random selection of 25 vehicles was measured, which yielded a sample mean of 42 miles per hour and a sample standard deviation of 6 miles per hour. The first step in solving this problem is to determine what data we have. According to the question prompt, the sample mean was 42 miles per hour. You'll notice I use x. This is because this is a sample mean. Similarly, s, or the sample standard deviation, was 6 miles per hour, and this was for a random selection of 25 vehicles, which is our n. In order to estimate the population mean speed, we will use this first set of equations. First, we'll have to estimate the standard error. Since we don't have the population standard deviation, this is simply an estimate based on the sample standard deviation. The equation for the estimate of the standard error is the standard deviation of the sample divided by the square root of n minus 1. In this case, that is equal to 6, our sample standard deviation, divided by the square root, which in Excel can be determined using the sqrt function, of n, or 25, minus 1. In this example, our estimate of the standard error is 1.22. Now that we have an estimate of the standard error, we can calculate the confidence interval, which is our estimate of the population mean, as the sample mean plus or minus t times the standard error. The problem provided a sample mean, and we just calculated our estimate of the standard error, and so the last step is to determine the t. In order to determine a t, we need to calculate the degrees of freedom and use that to find a t-value from a table in the back of our textbook. So our degrees of freedom are equal to n minus 1, in this case 24. Next, we look at the t-table in the back of the textbook to find our value of t. This table is found on page 471 of the text. To determine a t-value, we need to look for the row with the appropriate degrees of freedom and select the t-score appropriate for our level of significance. Our level of significance, or alpha, is equal to 1 minus the confidence level. Let's determine a population mean at the 95% confidence level, or 0.95. 1 minus 0.95 is 0.05, and so we'll focus on this column. If we scroll down to 24 degrees of freedom, we'll see that the t-score for a 0.05 alpha is equal to 1.711. And now we have all of the information we need to calculate a confidence interval. Our confidence interval is equal to our sample mean plus or minus our t-score times our estimate of the standard error. Our lower limit is equal to our sample mean minus the t-score times our estimate of the standard error, or 39.9. Our upper limit is equal to the mean plus our t-score times our estimate of the standard error. We can say with a 95% level of confidence that the population mean, or mu, is between 39.9 and 44.1 miles per hour. We can also calculate a confidence interval for other levels of confidence. For a 99% confidence interval, we look back at our table at the 0.01 column, which is 1 minus 0.99. And for 24 degrees of freedom, our t-score is 2.492. So, at the 99% confidence level, our interval lower limit is equal to the mean minus the t-score for our 99% confidence times the standard error. And our upper limit is equal to the mean plus our t-score times the estimate of the standard error. We can say with 99% confidence that the population mean is between 38.9 and 45.1 miles per hour. You'll notice that the 99% confidence interval is a larger interval than the 95% confidence interval. The more confident we are that our population mean is within our range, the larger that range has to be. So one way to check your work, if you're calculating multiple confidence intervals, is to verify that the range is larger for larger levels of confidence. We can also construct confidence intervals around proportions. You see this commonly around election season. The news will report that candidate A will receive, say, 55% of the vote, plus or minus some margin of error. This is based on asking a small sample who they'll vote for, and not asking everyone who they'll vote for. Using statistics, the pollsters generalize from a sample to the population. For this example, I'll use problem 29 from the textbook. This is a hypothetical example, which states, to estimate the proportion of troops who support the U.S. military's don't ask, don't tell policy of discharging people who are openly homosexual, which by the way has been repealed, a political researcher interviewed a random sample of 50 troops from the population at a particular army base. She found that 69% of the sample favored this policy. Again, the first step is to determine what information we have. And in this case, we have very little information. All we know is that 69% of the sample favored the policy of the 50 troops that were sampled. We'll use this second set of equations for calculating confidence intervals of proportions. Since these are for proportions represented by p in these formulas, the first thing we'll do is convert our percentage into a proportion. Proportion is simply equal to a percentage divided by 100. So our proportion for this problem is 0.69. The next step, much like calculating confidence intervals for means, is to calculate a standard error. The standard error for proportions is equal to the square root of the proportion times 1 minus the proportion over n. So we'll type equals SQRT for the square root of the proportion times 1 minus the proportion divided by our sample size. You'll notice that I have to include a fair number of parentheses in order to ensure that Excel calculates the standard error in the correct order. Specifically, I first want Excel to calculate 1 minus the proportion, then multiply it by the proportion, then divide by the sample size, and then finally take the square root. You could also do this in steps. For example, you could calculate 1 minus the proportion, then the proportion times 1 minus the proportion, then divide that by n, and then finally take the square root. Either way, we now have our proportion and the standard error of the proportion. The last step is to determine the z. Calculating confidence intervals for proportions uses the z distribution instead of the t distribution. As your book highlights, for a 95% confidence level, the z equals 1.96, and for a 99% confidence interval, z equals 2.58. So, for our 95% confidence interval, the lower limit is equal to our proportion minus 1.96, or our z, times the standard error of the proportion. Similarly, our upper limit is equal to our proportion plus 1.96 times our standard error of the proportion. This means that we can be 95% confident that the population proportion is between 0.56 and 0.82, or somewhere between 56 and 82% of the population supports the policy. For the 99% confidence interval, we do the same thing utilizing the z for a 99% confidence. So our lower limit is equal to our proportion minus 2.58 times the standard error, and our upper limit is equal to the proportion plus 2.58 times the standard error. We can be 99% confident that the population proportion that favors the policy is between 0.52 and 0.86, or we can be 99% confident that between 52 and 86% of the population favors the policy. Just as with confidence intervals for means, the larger the confidence, the larger the interval.